Hi class, welcome to this new video of tutorial 8, where together we will solve some questions on the tutorial. In this video, let's have a look first on tutorial 1, where a matrix A is given, and you are asked to check if any of these vectors 2, 1, 0, minus 2, 4, 1, 0, 0, 0, 1, minus 1, 2, 2, 2, 0, 1 are eigenvectors of A. And if they are, then list the corresponding eigenvalues. So we know that, okay, as a solution, we know that to find, to check the eigenvectors of a matrix for special eigenvalues, we need to solve the equation A minus lambda I V equals to 0, right? And this is equivalent to solving AV equals to lambda V. That is, V is the eigenvector for special eigenvalues, right? Now, so in our case, we have to check. Let's use the first vector. We have 8, 2, 2, 8, 2, 2, 2, 5, minus 4, 2, minus 4, 5, and then I do 1, 0. So multiplying this, right, this will give me 18, 9, 0, right? If you multiply that, you will have this, and then putting 9 in factor, you have that to 1, 0. So we can clearly see from this, we have found that AV equals to AV equals to 9V, right? Where 9 will be the eigenvalue, right? So we do so this vector therefore is an eigenvector corresponding to the eigenvalue 9. Okay, so if we check the second vector, we have 8, 2, 2, 2, 5, minus 4, 2, minus 4, 5, minus 2, 4, 1. So if you multiply this, right, you have minus 6, 12, minus 15. If we put 3 in factor, we have minus 2, 4, but we have minus 5. So you see that there is a difference. This the vector we are checking is minus 2, 4, and 1. But here we got minus 2, 4, and minus 5. So we can see that we don't have AV equals to lambda V. So this vector minus 2, 4, 1 is not eigenvector. Okay, so if you check the third one, 0, 0, 0, we know that 0, 0, 0 is not an eigenvector, right? This has been well defined in your lecture note, right? Because we define the eigenvector as a non-zero zero vector, right? So the zero vector is not an eigenvector, right? Okay, simply because an eigenvector is defined as a non-zero zero vector. Then if you check, if you also check the other vector, you have 8, 2, 2, 2, 5, minus 4, 2, minus 4, 5, right? If you check this one vector, you will have to multiply this, it will give you 0, 0, 0. So this will give you 0, minus 1, 2, 2. So this corresponds to a eigenvector for eigenvalue 0, right? And then if you do the same for the last vector, since you are checking, right? If you do the same for the last vector, since you are checking, this is 2, 0, 1, right? This will give you 18, 0, 9, right? Then put 9 factor 2, 0, 1. So you have that this obviously satisfy the AV equals to 9V. So we definitely have that 2, 1, 0 and 2, 0, 1 are eigenvectors corresponding to the value lambda equals to 9. And then we have minus 1, 2, 2 is also eigenvector corresponding, right, eigenvector corresponding to lambda equal to 0, and we have that minus 2, 4, 1 is not an eigenvector. Okay, so the next question is B. Decide if 3, 2, 1, 0, right, equal to 6, 0, 3 is an eigenvector of A. Okay, so how will you approach such a question? Now, we obviously see that it's true, right? It's yes. This equal to this is an eigen vector of of um of A. So we can prove that, right, by saying that if we have an eigenvector different from 0, right, and then we know that Ax equals to lambda, let's call it V. AV equals to lambda V. Sorry, let me just have it quickly here. AV equals to lambda V, right? If we consider a non-zero scalar alpha, then we know that alpha V is different from 0. Then we have that A alpha V, right, equal to alpha A V, which is equal to alpha lambda V, which is equal to lambda alpha V. So we have that A alpha V equals to lambda alpha V. Therefore, you can see that this is also an eigenvector. Alpha V is also an eigenvector of matrix alpha for a special value lambda. Therefore, this statement is true. Okay. Now you also ask to um, decide whether 201 plus 210, which is equal to 411, is an eigenvalue of A, right? So you can we can decide by answering easily that yes is the case. Why? Because the sum of two eigenvectors, right, of a matrix is again an eigenvector of that matrix, isn't it? Yes, and it's the case, right? Because the sum of two eigenvectors of a matrix is again an eigenvector if the two eigenvectors correspond to the same eigenvalue, right? And you can see the proof of this in your lecture note. Okay, can we have a look on the second exercises? Let's look at exercise 3. I will give some hints here. You have A equals to 1, 3, 2, 2. The first question is find the eigenvalue of A, right? You are asked to find eigenvalues of A. We know that to find the eigenvalue of A, we need to solve the equation determinant of A minus lambda I equals to 0. So to do this, we have 1 minus lambda 3, 2, 2 minus lambda, which equals to 1 minus lambda 2 minus lambda minus 6. So this will give me, right, this will give me 2 minus lambda minus 2 lambda plus lambda square minus 6, right, which is equals to lambda square minus 3 lambda minus 4. I can factorize this, right? So equal to 0. So from here, I have that lambda is minus 4 and lambda is 1. So the question now is, the second question is that, is A diagonalizable? Okay, so the answer is what? The answer is yes. And can you remember what we explained in the lecture video? So since A is a 2 times 2 matrix, right? And A has two distinct eigenvalues, right? Therefore, A will have two two distinct independent eigenvectors, right? Two dependent eigenvectors. Therefore, A will be diagonalizable. Okay, therefore A will be diagonalizable, right? So the third question is find an invertible matrix P and a diagonal matrix D. So the third question is that find P. We know that the matrix P is the matrix of the column of the eigen vectors. That is, we need to find P, and to do that, we need to find the eigen vectors of A. Now, let's look at the eigenvector for lambda equals to 4. We have to solve the equation A lambda I V equals to 0. And then I will have that it will give me that 1 minus 4, right? 3, 2, 2 minus 4, which is equals to minus 3, 3, 2 minus 2, right? So I can, when I see this, I can simply apply the Gauss reduction. R2 equals to R2 plus R1. So this will give me that minus 2, 2, 0, 0. And dividing everything by R1 divided by minus 3, I will have 1 minus 2 over 3, 0, 0, 0, right? Now, and I have the weighted matrix here, okay? Yeah. So this, therefore, from this equation, I will have that the x, I will have that v, the vector v, will give me right 3, 2. Okay. Now for lambda equal to minus 1, what I will have, the matrix will be 2, 2, 3, 3, right? Then I do a simplification. R1 divided by 2, R2 divided by 3. This gives me 1, 1, 1, 1, right? And if I do R2 equal to R2 minus R1, this will give me 1, 1, 0, 0, right? And from here, I will have that V equals to minus 1, 1. So I have the two eigenvector, therefore I can have the matrix P equal to 3, 2, minus 1, 1, and I have the diagonal matrix, which is the matrix the diagonal of the eigen values. So you can easily prove that this is P and this is D by doing the multiplication minus 1 AP equals to B. Thank you guys. I hope you enjoyed this video. Ciao.